Up until this point, our study of Newton's laws has focused only on a single object. In this video, we begin to look at systems that contain two or more objects and focus on a strategy where we either look at the system as a whole or we zoom in and look at one of the individual objects, and we see what the benefits of both perspectives can be. These two strategies of either looking at the system as a whole or looking at an individual block sort of get us to different goals of a problem. Typically, if we are looking for the acceleration of either a single object or the whole system, we will look at the system as a whole. And we will ignore sort of the connections between the objects, at least the forces that deal with those connections. If instead we're looking for an internal force, which is going to be something like tension, then we'll have to focus in on an individual object like a block and apply our ideas of Newton's laws to just that block. This slide will come up again later in the video, so if you need to write some more information down, you can take a look at it then. Let's take a look at an example here, but before we do, we're going to look at kind of a simple situation, and then we're going to see how that can help us understand this more complex situation. All right, so hopefully this picture is very straightforward. We're frictionless. We have a pulling force of 2.4 newtons, so that's going to be this arrow that's pictured here. This is really a very straightforward problem. If we want to find the acceleration, we would just use Newton's second law, F equals ma, and our net force is actually just a single force of 2.4 newtons. Our mass is 6 kilograms, and then our acceleration is our unknown. So again, nothing too complex with this particular problem. But this is going to help us understand a more complex system in that we will turn a complex system into something simple like this. So here's a typical system of two blocks. You might think of it sort of like a train, where you have two objects that are connected, in this case, by a rope, and then the whole system is being pulled forward, again, by 2.4 newtons. So notice that the total mass of the system is still 6 kilograms, like it was in the previous problem. It's just that those 6 kilograms are split between two boxes. But everything is happening the same to those two boxes. They're both being pulled along this horizontal surface. And so if we want to find the acceleration of the box, we sort of each box, we really just sort of ignore the fact that this rope is between them. We really just sort of think about the system as a whole and think about the whole system moving forward at 2.4 newtons. And since it's the same 6 kilograms that we just solved, our acceleration would again be 0.4 meters per second squared. So the idea here is that ignoring the connections and just sort of looking at the whole system can allow us to find the acceleration of everything and each individual part all at once. In words, this is what I'm talking about. If we want to find that acceleration, we're going to look at the whole system in almost every case. Big idea. But what if we do want to find tension? What if we do want to find the force that's pulling forward on the 4 kilogram object and pulling back on the 2 kilogram object? How could we find that tension? We can't keep looking at the whole system because for the system, these forces are canceling each other out. A rope will have the same amount of force pulling one way as it pulls the other way. Any section of rope will have the same tension no matter if I'm looking at the connection over here or the connection over here. So if I were to add up all these forces, it would just be 2.4 minus t plus t. It's still just 2.4. The the tension forces are referred to as internal forces, and they don't show up in our calculations if we look at the whole system. Instead, we need to look at an individual block. So let's take a look at this front block for starters here, and I've placed a box around it. That's something you can use in your work as well to help you focus in only on a single part of the system. The key thing, though, is that we have already found the acceleration, that 0.4 meters per second squared, and that's the value for each individual block as well as the whole system. So now I have this value to sort of add into the given info. And if I just focus in on this 2 kilogram block, going back to Newton's second law, I can say that the forward force is 2.4 and the backward force is this tension T, and that determines just this mass times my acceleration. This is a very key point here. I've zoomed in on just a part of the system, and so I can only use that mass in my setup. As I work my way through here, then we get 2.4 minus T is equal to 0.8, and so our tension force ends up being 1.6. Now that tension again is the same whether I'm talking about the pull backward on this block or if I switch and I talk about the pull forward on this block. Let's prove that to ourselves by changing our focus. If instead we zoom in on just the 4 kilogram block and ignore everything else, the 2.4 Newton force is not going to be included, because that's outside this little subsystem that I'm looking at. The only force that is acting directly on the 4 kilogram block is the tension force. And so when I write F equals ma for this block, tension is the net force. It's the only force pulling on this object. Its mass is 4. Again, my acceleration is still 0.4. That I found looking at the whole system, and it continues to be useful throughout the whole problem. Notice again that the tension comes out to be 1.6 newtons. So whether I look at the 2 kilogram block or the 4 kilogram block, I get the same value of tension through my calculations. All right, one more review then. The strategies we're going to use when working with more than one mass is we will look at the whole system if I'm looking for something like the acceleration, because the acceleration is the same for the entire system. If I am looking for something internal, like tension, then I'm going to have to look at an individual block, because internal forces come in pairs, and so they cancel out when you look at the whole system.